Assalamualaikum and hi everyone. So in this video we are going to talk about the application of first order differential equation. The application of first order differential equation. So we are going to solve for Newton's law of cooling. So what is the Newton law of cooling? According to Newton's empirical law of cooling or warming, the rate at which the temperature of a body changes is proportional to the difference between the temperature of the body and the temperature surrounding medium. So according to the Newton, the rate of change. So when we say the rate of change, usually we associate rate with time. So rate of change of body temperature. So let's say we use the capital T to represent the temperature of the body. So when we say the rate change of temperature, that means dt over time, dt over dt. So this is proportional. This rate is proportional. So proportional is this symbol. The proportional to the difference between the temperature of the body. So difference between temperature of the body. So difference between temperature of this body and the temperature of the surrounding medium. Let we denote the surrounding medium as Tm. So now we have a mathematical statement. The rate of changes of temperature, body temperature. So this is the rate of changes of body temperature is proportional. So this symbol between the temperature of the body and the temperature of the surrounding medium. So now we have a mathematical statement or mathematical expression in terms of differential equation. So we need to convert this mathematical statement into mathematical equation. So when we say proportional, so what is the meaning of proportional? So the meaning of proportional is one variable increase, so then the other variable. So in this case, we have temperature of the body and the difference between the temperature of this body and the surrounding medium. So when this one is bigger, that so the temperature of the body also became bigger. So when we want to change this mathematical expression into mathematical equation, we substitute the terms of proportional to the symbol of equal, and because we know that this is just a linear relationship, so let's put a constant linear k, t minus tm. So usually when we are using the constants of proportional k, so we associate this with negative. You will find in other textbooks sometimes we use positive constant k or negative constant k. So in this case we are using the negative constant k, constants of proportional. So now we have one differential equation relating the temperature of the rate of temperature dt over dt, and this rate relating to the difference between the temperature of the body and the surrounding medium. So because we have this differential equation, this differential equation, actually we can solve it by using a separable equation or linear equation. Let's find the solution to this problem. So we have a differential equation, the rate of change, so dt over dt are equal to negative k t minus tm. So this equation are separable. You can solve it by separable equation, and this equation are also linear. So you can use a separable equation or linear equation to find the solution for this problem. So in this exercise or in this video, I will use a separable equation to solve this differential equation. So we need to separate the variable time and the variable T, temperature of the body and the variable of time. So in this mathematical equation, we have one variable here, T minus Tm. So these are going to be a variable for time. And here also we didn't find any variable in this right hand side, variable relating to the T. So we left by negative k. So let's separate the variable. So divide everything by t minus tm. So we have 1 minus t minus tm, and multiply both sides by dt. So we have negative k multiply dt. So now we have separate the variable. Integrate both sides of the equation. So we have left hand side will be ln t minus tm, right hand side, because we are integrating with respect to time, so we will get kt and plus c. So this is the solution. So this solution we can simplify by taking exponent both sides. So when we are taking exponent on the left hand side, so exponent ln equal to 1, we cancel each other, so we have t minus tm, while the right hand side we have exponent negative kt plus c. Further can be simplified as exponent kt multiply exponent c, and exponent c is just a constant, so let's replace this by constant a, exponent kt, and the left hand side equal to t, so minus so plus tm here. So this is our solution for the Newton's law of cooling. So in this solution, there are two unknown variables. First, we didn't know what is a, and secondly, we didn't know a constant of proportional k, constant proportionality k. So we need to find these two values before we can use this equation to solve any problem relating to the Newton's law of cooling or warming. So remember this equation, remember how you can derive from this equation to this equation. If you are asked to derive this equation, you can use this solution. You also can use a linear equation to find the solution for Newton's law of cooling. Let's see example number 12. A bowl of soup is put from a pot contain 95 degree into non-insulated bowl in a room at 20 degree. After 2 minutes, the soup has cooled to 80 degree. How much time is required for the soup to reach an eatable temperature at, let's make a correction here, at 50 degree. Alright, so to solve this equation, to solve this problem, first let's jot down what is the information that we have from the question. So first thing is, we know that the soup, initially the temperature are 95 degrees, so we put T naught equal to 95 degree. After 2 minutes, so the soup has cooled to 80 degrees. So after 2 minutes, let's put 80 degree, and the room temperature at the time was 20 degrees. So Tm is 20 degree. So all these are information we need. So how much time is required for the soup to reach an eatable temperature at 50 degrees? So we are going to use all this information to find the constant of a and the constant of negative k. Before we can solve it, the time to reach 50 degree. Alright, so by using the information that we have so far, we know that the temperature is equal to A exponent negative kT plus Tm. So we know that A equal to exponent negative kT plus 20 degree. First, we can use this information at T naught. At T equal to 0, time equal to 0, the temperature is 95 degree. So when T equal to 0, T equal to 95. So 95 equal to A exponent negative K times 0 plus 20. So 95 minus 20, 75 equal to A exponent 0. Exponent 0 is 1, hence A is 75. So we have T equal to 75 exponent negative kT plus 20. Now, when time equal to 2, the temperature is 80. So 80 equal to 75 exponent negative k times 2 plus 20. So 80 minus 20, 60 equal to 75 exponent negative 2k. So let's continue next slide. 60 equal to 75 exponent negative 2k. So 60 divided by 75 equal to exponent negative 2k. Take ln both sides. So ln 60 over 75 equal to exponent 2k. Hence k equal to ln 60 over 75 divided by minus 2. So using the calculator, so we found the value for k, 0.116. So T equal to 75 exponent negative 0.1116T plus 20 degree. Alright, so the initial question was, what is the time when the temperature reach 50 degree? So substitute all the information we have. When time equal to 50 degree, so 50 degree are equal to 75 exponent negative 0.1116T plus 20. So 30, 75 exponent negative 0.1160, 30 over 75 equal to exponent negative 0.1160. Take ln both sides, so ln 30 over 75 are equal to negative 0.1160. So T are equal to ln 30 over 75 divided by negative 0.1116. So this is about, this is about 8.21 minutes. So the conclusion is the soup reached an eatable temperature after approximately 8.21 minutes. So this is our final answer. Example 13. A body of an apparent homicide victim was found in a room that was kept at a constant temperature 70 degrees Fahrenheit. At 12 noon, the temperature of the body was 80 degrees Fahrenheit, and 1 p.m. it was 75 degrees Fahrenheit. Assume that the body of at the time of death is 98.6 Fahrenheit. Determine the time of death. So this is a problem of Newton's law of cooling. First, we have a equation for Newton's law of cooling. The equation that we have just derived was T equal to A exponent negative KT plus Tm. So what is the information we have here? So the information that we have is a body of an apparent homicide victim was found in a room that was kept constant at temperature 70 degrees Fahrenheit. So this is the room temperature, which is 70. The room was 70 degrees. And at 12 noon, the body was 80 degrees Fahrenheit, and at 1 p.m. it was 75 degrees. So initially, when the body was found, it was 80 degrees Fahrenheit, and after 1 p.m. it was 75 degrees. And assuming that the body of temperature at the time of death is 98 degree, 98.6 degree, determine the time of death. So we want to find what time the body was found. When the body was found, it was 98.6 degree. So now let's use this information. So the body was, let's say, at 12 noon. We take this at 12 noon as T note. At T note, we found that the body was 80 degree. Initially, the body was 98.6, but because we didn't know what time of death, so we are using at 12 noon the body was 80 degree, and after 1 hour the body was 75. So we are going back in time to find out what the time was when the body at 98.6 degree. So now by using all this information, we can find the constant for A and negative K. So initially at T equal to 0, the temperature was 80 degree. So 80 degree are equal to A exponent negative KT plus 10. Tm is 10. Tm is 70, sorry. Tm is 70, so 80 minus 70 is 10. T is 0, so the T is 0, so we have A exponent 0, which is A equal to 10. So we have 10 exponent negative KT plus 70. Now, when T equal to 1, the temperature of the body was 75 degree Fahrenheit. So 75 equal to 10 exponent negative K times 1 plus 70. So 75 minus 70 is equal to 5. 10 exponent negative K So 5 divided by 10 equal to exponent negative k ln 5 over 10 equal to negative k. So k is negative ln 5 over 10. So k is 0.6931. So now we have t equal to a, where a is 10 exponent negative k 0.6931 times t plus tm. Tm is 70. So this is the full equation for temperature of the body. So now we want to find what is the time when the temperature of the body was 98.6 degree. So remember that this is the initially temperature of the body. So initially it was found at 98 degree, but we know that when the temperature of the body at 80 degree, the time was 12 noon. This is 12 p.m. So we want to find what is this time. What is the time when the body was at this temperature, and then we can minus from the time 12 p.m. to find the time. Alright, so we want to find what is the time when temperature was 98.6 degrees. So 10 exponent negative 0.9631 t plus 70. So 98.6 minus 70, 28.6 equal to 10 exponent negative 0.96931 t. So divide by 10, 2.86 equal to exponent negative 0.6931 t. Exponent, so take a ln 2.86 equal to negative 0.6931 t. So t are equal to ln 2.86 divided by negative 0.6931. Negative 1.516 hour. So now we have a time. It was 1.61. It was negative 1.516 hour before 12 noon. Negative mean before 12 noon. So convert this into hours and minute. So 1 hour plus 0.516 times 60 minutes. So this was about 1 hour 31 minutes. This was about 1 hour 31 minutes. So this is equal to 0.516 times 60. This was about 30.96 minutes. Let's use 31 minutes. So 1 hour 31 minutes before 12 noon. So we have a 12 noon minus 1 hour 31 minutes. So this one will be 60. So 60 minus 31, 29, 11 minus 1, 10. So the body was found at 10:29 minutes. Ten 29 a.m. The time of that was 10:29 a.m. Alright, that's it for the applications of Newton's law of cooling. Then you can do this exercise to find out whether you understand or not about this Newton's law of cooling. With that, thank you.